Okay, welcome to our first day of math learning. So in ALEKS, we are going to be doing 1R 1.1. That just means that we're in chapter 1 of a regular class. This is secondary 1 regular. And then we are doing assignment 1.1, chapter 1, assignment 1. And hopefully most of this is review. A lot of it has to do, actually I think all of it has to do with decimals. So if I had the number 4,621.1348, what number is in the tens position? Just yell it out. 2 tens position. So this is the tens position. And we're based off of a decimal system. And you guys think that that is what decimal means? And you're kind of right. But decimal actually means we're using a number system with 10 digits. Deci being 10 in Latin. Okay? You can do a hexagon or an octal or a hexal system. So in a decimal system, we have the numbers 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 10 of them. So the word decimal means the number system that uses 10 digits. Okay? You guys get that? All right, what if I used, so we also call this base 10. What if I did base 5? Let's count in base 5. 1. Oh, so base 5 is 0, 1, 2, 3, and 4. Okay, so I'm counting 1, 2, 3, 4. What comes next? There is no 5. Right? The number 5 does not exist. There's no 6 either. So what happens in decimal when we run out of numbers? You go to the next level. So the next number is 10. Now what? 11, 12, close, 13, 14. I don't have a 5. 20. 21, 22, 23, 24, 30. Okay, so let's say 47. Oh, wait, we don't have a 7. 42, 43, 44, 50 does not exist because I don't have a 5. 60 doesn't exist, I don't have a 6. 100. Okay, now I want to show you something. This number right here, and what we do is we usually say 13 base 5. We kind of put a little note on it so we know what we're looking at. If it's base 10, we don't. 13 base 5 is the same as 1, 2, 3, 4, 5, 6, 7, 8. So 13 base 5 is the same as 8 base 10. Okay? What if I did base 3? For base 3, what would my numbers be? 0, 1, and 2. Okay, so let's count. 1, 2, there's no 3. 10, 11, 12, 20, 21, 22, 100. Oh my gosh. Your mind's going to explode. Good job, Money. So those numbers are all the same. Okay? Now, mathematically, base 10 is kind of a bad idea. Base 12 is a better idea. So, have you ever wondered why a circle has 360 degrees? Where did that come from? 360. Right? Why not 200? Why not 1,000 degrees? Why 360? Well, the reason is lion, sun, whatever. So, when the Earth travels around the sun, how long does it take? 365. And actually, it's not 365. It's 365.25. Yes. How does leap year work into that? Did you guys understand that? So here's planet Earth, okay? Whoop. And we wait a whole year. We go all the way around. We go all the way around, and then we go a little bit too far. Right? We went a little bit further than one revolution. Okay? And then the next year, we go all the way around again, and a little bit too far, and then a little bit too far, and the next year we would be so far that the distance from here to here is 1 day. Right? So then we have leap year. What does that do? It crams a day in there, and it kind of resets us back so that the next go around we land right here again. Okay? But I kind of lied to you. It's not actually 365.25. It's 365.24 something something something. Which means is it irrational? It probably is. It probably is, simply for the fact that irrational numbers are more common than rational numbers. So probably, but I don't even know if we know the answer to that. So guess what? Every couple hundred years we skip leap year. Because it's not a quarter of a year extra, it's a little bit less than that. So if we do leap year every 4 years, we're actually going to be every 100 years we're going to be a little bit ahead, a day ahead. So we have to backtrack. And in 2000 there was no leap year, even though it was supposed to be a leap year, because it's 0.24, it's not 0.25, so it's off by 1/100th. Yes. Yeah. Yeah, if you're a leap day baby, you skipped it in 2000. And it's not every 100 years. It's like there will be, in 2000 we'll have it, and then 2100 we'll have it, and then we'll skip it, then we'll skip it at 2200 we have it, because it's not exactly 0.24. Okay? So, why 360 degrees? Well, this number, let's get rid of that. This number is not very friendly. It doesn't have very many factors. So 365 divided by 5 is 73, and 73 is prime. Okay? And numbers that have very few factors create more fractions. Right? For instance, the number 24. You can divide 24 by lots of numbers and avoid fractions. You could divide by 2, 3, 4, 8, and 12. And numbers that have lots of factors are very friendly because that eliminates fractions. So if we did 365 degrees in a circle, we would have fractions all over the place that we don't want to do. So instead, we divided by 360. And 360 has lots of factors. 2, 3, 4, 5, 6, 8, 10, 12, 15, 18, 20, 24, and then a lot more, right? Like it would have 360 divided by 2 is 180. 360 divided by 3 is 120. 360 divided by 4 is 90. And then there's some more in the middle, right? We chose 360 on purpose. And we chose it because it has a ton of factors. So you can take a circle and divide it into all sorts of pieces and still have whole numbers, right? You can cut a circle into 120 pieces, or 3, or 5, or 8, or 10, or 12, 15, 18, 20. It's just more friendly. Okay? Well, why do I bring that up? Well, how many factors does 10 have? 2. Right? 2 and 5. Okay? And because of that, base 10 has more fractions than some other bases. A good base would be base 12, and we'll get to that in just a second. Okay? All right. What about base 2? What would that look like? So let's count in base 2. 1, 10, 11. Nope, there's no 2. There's no 2. 100. 101. 110. 111. No 2. 1000. 1001. 1010. 1011. And then 10,000. Does that look familiar? Oh, I skipped some. Sorry. There we go. I skipped 2. Thanks, Money. Does that look familiar? That's binary code. Why is it called binary? Bi is the prefix for 2. So binary has 2 numbers. Okay? What uses binary? Computers. Why do computers use binary? It's not because of fractions. It's because computers, they're more complicated now, but they used to just be little switches, like light switches. And the switch was either on or off. So off was a 0 and on was a 1. And so you could make numbers by turning different things on and off, and computers still use binary to save things. But look at this. So 13 base 5 and 8 base 10 and 22 base 3 and 1000 base 2 are all the same number. Okay. You need to quit with your mask. It's okay. First 2 are free. What was your question? No. So this is decimal. Decimal just means base 10. Now, you guys are used to calling these decimals, which is true, right? So decimal kind of has two meanings. It really means base 10, but we have turned it into those numbers that come after the period. Okay, well, a better base, oops, let's not do it that way. A better base would be base 12. Why would base 12 be a good idea? Yeah, factors 2, 3, 4, 6. It has a lot more factors, and how does that help us? We have fewer fractions. In fact, if we were to switch from base 10 to base 12, half of all the fractions we run into would disappear, because base 12 has twice as many factors as base 10. But what would base 12 look like? Well, what would the 11th number be? Well, it can't be 11, right? We can't do this, because that's two symbols in base 10. We need one symbol that represents the number, and actually it would be a 10. We have to make a new number, exactly. And so I don't know what that number would look like, but let's call it fancy E. Actually, that's not what they do, sorry. It's actually a fancy T for 10. Okay? And then the next number would have to be, I'm going to do fancy E. Now you look at that and say, wait a minute, those are letters, not numbers. But our numbers are just symbols. You're just used to them. So let's count in base 12. 6, oh wait, I better start at the beginning. 1, 2, 3, 4, 5, 6, 7, 8, 9, fancy T, fancy E, 10, 11, 12. So let's wait a minute. So, okay, we're in 8, base 10. Okay. So 11, 12, ... 19, oops, it won't let me write on that. 19, fancy T-teen, fancy E-teen, 20. You guys get that? Okay, so 26, 27, 28, 29, 20 fancy T, 20 fancy E. Does that make sense? Okay, so 98, 99, 90 fancy T, 90 fancy E. Nope, not 100. Nope. Fancy T100, T100. I don't know how you'd say it. Right? So, fancy T8, fancy T9, fancy T, fancy T, fancy T, fancy E, E100. Oh, yeah. No, I did it. I did the T and the E. Okay, does that blow your mind a little bit? But do you understand the structure of a base system now? And you can change it to whatever you want, and computers use binary because it's just simpler. It turns out we only need two numbers, a 0 and a 1. As long as you have a 0 and a 1, you've got everything. Okay? All right, so going back to my original question, we found the tens place right there. What do we call this place? The thousands. Okay? And that's thousands in any base system. But we're using the decimal system, which means we have 10 digits. Okay? What do we call this place? That is the hundredths place. But wait a minute, there are only 2 digits. So we call this the ones. This is the tens. This is the hundreds. And this is the thousands. Okay? What do we call this? Tens. Why the tenths? Let me write that out because it's hard to hear. The tenths. Why isn't it the oneths? Okay, the ones are somewhere else. What? It's 1/10 of 1. You can't have a oneth. There's no oneth. Right? If you have a oneth, it's a whole. It's not split into pieces. So on the left side of the decimal, we start with ones, but on the right side of the decimal, we have to start with tens. So this right here is a portion of a 1. So we can't call it a oneth. And how many portions are we cutting each piece into? 10. And then we cut those tenths, into tens, and we end up with, these are hundreds. Even though there are only 2 digits. 100 has 3 digits. But hundredths only have 2 digits because how many hundredths can you squeeze into 2 digits? Plus 99 plus 0 is 100, right? That's why the names don't match up on both sides of the decimal point. Okay? All right, so, and then this would be called thousandth, and this would be called 10,000ths. Okay? All right, let's, that's weird. Huh. Why won't it? Not what I'm used to. All right. So let's say we had 148.1263. Okay. Round this to the nearest tenth. What does that mean? So we find the tenths column. So this is the tenths. Okay. How do we round? Which number? The number after, right? So if the number after is 5 to 9, and by rounding up you mean the tenths we're looking at goes up by 1. Okay? What if the number after is below 5? It just stays the same. Why would we do this? Why do we round? Yeah, if that number goes on forever, we don't want to write it all the way out. Okay? So why don't we just cut it off and throw it away? Yeah. But would we be okay if we just cut it off and then ran away? Well, what if I just said, I'll just throw this stuff out. I don't need it. Well, in this case, that's not going to be so bad, right? So rounding this to the nearest tenth, oops. So I look at the 1, and then I go to the next one after, so the 2. That 2 is smaller than 5, which means, do we round down? We just keep this 1 the same. So the answer would be 148.1. Okay? All right. What if I rounded to the nearest hundredth? Okay. So I look at the hundredth place. Oops. Right here. And then I look at the one after it. And that 6 is bigger than 5. So I'm going to change this one by 1, and I'm going to say 148.13. Okay? So to round, you look at the number you want to round, then you go 1 to the right. If the 1 to the right is bigger than 5, then you make your number bigger by 1. Now, why? Why do we do that? Why don't I just say 148.12 and then call it good? Why bother rounding at all? Not sure. I don't think I follow. Oh, I see. Oh, I see. So we want to shorten the number to make our lives easier. Okay, yes, totally. But why bother with even looking at this stuff? Why don't we just delete it and stick with that number instead of rounding it to this number? Right. Why is this more accurate? Because this number, this is closer to that than it is to this. Do you want me to give you an example? Let's say you own Walmart and you're selling a pair of flip-flops. And the flip-flops are $3.99. And somebody comes in and says, I'm going to round that to the nearest dollar. It should be $4, right? What if that person doesn't obey the laws of rounding and they just say, I'm just going to delete this? Then you're 99 cents off. So rounding is a way to make our lives easier, but to be more accurate, we need to list the dollar value or whatever value it is that's more accurate. That's how we do the laws of rounding. Okay. That is weird. Huh. Oh well. Not sure why it's not working today. Okay. So what if I had 58.794 and I wanted to round to the nearest hundredth? What would the answer be? 58.79. Why? The 4 is smaller than 5, so we keep the number we're looking at the same. All right. What if I change this to a 6? So 58.710. Right? That number doesn't exist. Well, it does exist, but it's totally wrong. So this is instructing me to make the 9 bigger. So we turn the 9 into a 10. So that's going to add 1 to the 7, and it's actually 58.8. And we wanted to round to the nearest hundredth, which is this space. What number is really there? That number is 0. And actually, you can write as many zeros as you want. But we're lazy. We don't write those. For the same reason that we don't put zeros out here. Does that make sense? Okay. Rounding, rounding, rounding. All right. So, if you have not finished your knowledge check, do your knowledge check. Once you're done, I want you to do 1R 1.1. Okay? If you don't get that done in class, then can you please log in at home and finish at home? We good? Okay, get to work.